my name is Garvit Shubham. I am a second year BTech CSE student at Bennett University, and today I will be explaining Boruvka's algorithm. Boruvka's algorithm is a greedy algorithm, just like Kruskal's and Prim's. A greedy algorithm is, as we know, is an algorithmic paradigm that builds up a solution piece by piece, always choosing the next piece that offers the most obvious and immediate benefit. So the problems where choosing locally optimal also leads to global solution are the best for greedy. So here Borukka's is an, of course, just as I said, is a minimum spanning tree algorithm, just like Kruskal's and Prim's. So the steps for Borukka's algorithm are similarly, first of all, we take the input, then we initialize all vertices as individual components, then we initialize the MST as an empty tree, then we take out, while there are more than one components, we find first of all we find the closest weight edge that connects this component to any other component, and then we add this closest edge to MST if not already added, and finally we repeat this, of course, and then finally we return the MST. Now to explain this further, I will take an example. So first of all, we will take a graph, for example, and let's take it as 0, 1, 2, 8, 7, 4, 5, 9. So this is a graph, and taking on the weights, it will be 4, 8, 11, 8 again, 7, 1, 6, 2, 7, 4, 14, 9, 10, and 2. So this is our initial graph. Now we'll be initializing an empty MST. The MST will be empty, and every vertex we will be taking it as a single component. So for that, it will be like this 0 will be a individual component, 1 will be an individual component, 2 will be an individual component, 3 will be an individual component, and so on. Every one of these nodes will be taken as an individual component. And now for every component, we will find the cheapest edge that connects it to some other component. So if we take it from this, it will be like, for let's say component, and the cheapest edge. So if we take the component as 0, the cheapest edge here would be 0 to 1, this one, as it is 4, while the other one, 0 to 7, is 8. So therefore the cheapest edge for 0 is 0 to 1. Similarly, taking on for 1, the cheapest is of course again 0 to 1. Similarly, since 8 and 11 are greater than 4, and for 2, if we look at, the cheapest edge will be with 8 here, which is 2. The weight is 2, so it's 2 to 8. Now moving on to 3, we will get 2 to 3 again. There is sorry, 2 to 3, not again, my bad. So 2 to 3 is 7, while 3 to 4 is 9, and 3 to 5 is 14. So we get the idea. So we get 2 to 3. So now moving on to 4, we get for 4, we find 14 is now 10 is of course greater than 9, so therefore this 3 to 4 is the cheapest edge. Now let's see if it is 5, 6, 7, 8. So this is 5 to 6, this here is 6 to 7, again 6 to 7, and 2 to 8. Now we can clearly see it from here. For 6 to 7 is 1, of course, so this one is, as we saw for both 6 and 7, is the cheapest edge. 2 to 8 is also the cheapest edge, which we already decided. And we also got 5 to 6 as the cheapest edge for 5. So these are the cheapest edges that we have. So after this, we will get our MST, which was previously empty, as a set of 0, 1, 2, 8, 2, 3, 3, 4, 5, 6, and 6, 7. Now after what we did before, the components will also become a set. So the sets will be, as you can see, the first will be 0 to 1, this set. The second set will be A, 2, 3, 4, this one. And the final one, the final set component would be 5, 6, and 7. Now the thing we did for individual components for every single node, we will do for these set components. So repeating the step again, let's get back here. Now for the better understanding of the second step, let's draw the graph once again with these components, the set components clearer. Now 0, 1, 7, 2, 8, 6, 3, 4, and 5. So now recalling the one which are our components for the next step, it is 0 to 1, 2 to 8, 2 to 3, 3 to 4, 5 to 6, and 6 to 7. The rest we will connect with white to make it easier for us to understand. And 2 to 5, and 7 to 8, and 0 to 7, of course. So this is 4, this is 8, this is 11, 8, 7, 1, 2, 4, 7, 6, 2, 14, 9, and 10. Now again we will move forward to the repeating the step, which is components here and cheapest edge. Here our components are 0, 1, and the cheapest edge will be 1 to 2, as we can see here. Now the second component will be 2, 3, 4, 8. 3, 4, 8, and the nearest edge to it will be 2 to 5, which is 4. As you can see here, in the next step we will be able to see it clearly. The 0, 1 set will be added to the 8 through 3, 4 set. But here it is the cheapest is of course 2 to 5, and for the last set it is 5, 6, 7, and the cheapest edge to this will be 2 to 5 again, as it is 4. So 2, 5. So after this step, the MST will become as 0, 1, 2, 8, 2, 3, 3, 4, 5, 6, 6, 7, 1, 2, and 2, 5. So the MST will totally include, it will include 0, 1, it will include 1, 2, it will include 2, 8, it will include 2, 5, 2, 3, 3, 4, 5, 6, 6, 7, and 2, 5, as I said. Now this has become a bit congested, so let me draw it as a final stage, because as you can see all our nodes, we have a way to join all our nodes with this MST. So again, the cheapest edges graph would be something like 0, 1, 2, 3, 4, 5, 6, 7, 8. 0, 1, 1, 2, 2, 3, 3, 4, 2, 5, 2, 8, 5, 6, 6, 7. Now this is 9, 7, 4, 2, 2, 1, 4, 8. This is a currently joined MST. So at this stage, the components we have, let's figure out the components we have. So the component is 0, 1, 2, 3, 4, 5, 6, 7, 8. As you can see clearly, the present MST, we only have one component left. As we said, the MST is 0, 1, 2, 8, 2, 3, 3, 4, 5, 6, 6, 7, 1, 2, 2, 5. And the component is at this stage is 0, 1, 2, 3, 4, 5, 6, 7, 8. So basically all the edges are there. So at this position we stop our process and return the MST. And so for this, as the final MST we have is 0, 1, 2, 8, 2 3 3 4 5 5 6 6 7 1 2 and 2 5. So as it's a minimum span tree, the minimum count of minimum weight of the edges will of course be the sum of every one of these components of MST. So which will be, so minimum weight which we are here to find will be equal to 4 of 0 1 for 2 4 plus 2 of 2 8 plus 7 for 2 3, and then we have a 3 4. So for 3 4 it's plus 9. For 5 6 we have plus 2. For 6 7 we have plus 1. For 1 and 2 we have plus 8, and finally for 2 and 5 is plus 4. So we get our total as for minimum weight will be 4 plus 2 is 6, 6 plus 7 is 13, 13 plus 9 is 22, plus 2 is 24, plus 1 25, plus 8 is 33, plus 4 is 37. This will be the answer we will get. Now the time complexity for this algorithm is similar to Kruskal's and Prim's, which is time complexity is equal to big O E log V, where V are the vertices and E are the edges. This was me explaining Boruvka's algorithm. Thank you for viewing.